Siva Yellamraju sold 3 startups to tech giants like Apple and Google. But instead of riding the AI wave, he pivoted to solve energy resilience, one of the toughest problems of our time.
Why not go after bold problems, bigger problems that people think are beyond reach sometimes, but solve them like any other engineering problem?
His focus, hydrogen, a molecule long promised but never quite delivered. His approach, engineering audacity.
Any problem can be solved if you apply an engineering mindset to it.
Siva and his team reimagined hydrogen from the ground up. Data center principles applied to the physics of molecules. Modular, software-defined hydrogen plates. It turns the old equation on its head.
It's easy to move electrons and then atoms, so why don't we just generate it locally wherever it's needed?
Václav Smil has called hydrogen an energy trap. There's 60 to 70% loss of energy round trip.
If you look at only efficiency and that's your only metric, I think it defeats the purpose of looking at the problem holistically. At Fourier, we are all about that fundamental friction or balance between boldness and practicality.
Siva, welcome to On Climate.
Thanks for inviting me, Kathy.
Yeah, great to have you. So your journey fascinates me. You've had the dream Silicon Valley setup, multiple AI startups that got acquired by tech giants like Google and Apple, and you gave that all up to go solve energy resilience, which arguably is one of the hardest problems of our generation. But before we dive into Fourier, I'd love to maybe hear about your story leading up to Fourier.
I grew up in India in a very typical middle-class family, South India. But I fell in love with computers very, very young, maybe in 7th or 8th grade. And back then, it barely had a computer where I grew up, a small town. Fell in love with programming, and that's all I wanted to do. Eventually did my undergrad in computer science in one of the IITs in India. Came here originally from a grad school, but I also wanted to start a company pretty much. And pretty much since I came here since college, I worked on 3 startups before this. The first one, we were building a video conferencing software, which got bought by Polycom. Second one, we actually were doing one of the first applications of deep AI on video understanding and eventually became search at YouTube or Google. And most recently, we had other startup where we were building a smart speaker with a 360-degree camera that eventually got merged with Apple. So yeah, like you said, I would say more, if I can call that, it's a pretty traditional Valley tech background. Worked on deep AI, some consumer hardware problems, enterprise software. But I really grew up really wanting to be a computer engineer. So, and then I'm really happy that I work and continue to work on something that I've always been passionate about personally too. So yeah, I'm an engineer and left Apple about 4 years ago. Just decided that I wanted to work on energy, and we can talk about why energy doesn't feel to me as a transition, but that's my background.
So you've said it's time to stop imagining a better world and start engineering it. I guess that's your inspiration to Fourier. Let's dive in.
That's right. I mean, the line itself was something that we were discussing, and now it became everything on the website. But the fundamental motivation for me is, as an engineer, I always, whenever I looked at each company that I've worked on, there was always engineering curiosity that drove me. You look at an interesting problem, and then you think of, okay, this sounds interesting. Let me go solve it, and that's how the typical builder mindset works. That is still true, but I think over time perspectives change. We keep talking about the problems with the way we are doing many things in the current world and how we can do better. We see it in movies. We talk about it. But either you think of those problems as something that's way in the future that we don't get affected by it, or most people think that these are hard problems that require complex compromises that most people don't take them upon. And there are other class of people who would be like, see them as research problems and work on it for years before they become realization. If there's one thing that being in startups in the Valley taught me, you can only solve these problems with just practical engineering. Any problem can be solved if you apply an engineering mindset to it. Then you break it down. I mean, that's what we engineers do. You break a problem down into meaningful pieces, the pieces that can be solved incrementally, and then you get to solve a problem. So I figure I thought I got to a point in my career where, well, it's not enough if I start working on another small step in an industry like, a video or something like that. But why not go after bold problems, bigger problems that people think are beyond reach sometimes, but solve them with like any other engineering problem? I mean, that's how we solved internet. That's how we solved AI, or we're solving AI. Why not energy? It's the same. Why don't we approach any problem with the same mindset? So that's what it means to me. You want to go after big problems, but you also want to go after them with a very practical engineering mindset that you can actually make it better. You don't want to ask people to compromise anything. You just want to make things better. People automatically use it. That's how any new invention that we had, we solve. So I mean, without taking 100 examples from the past, that's what been missing, I think, in especially when we look at energy and climate problems. And I thought, well, at least let me give it a shot. And that was one of the primary motivations for me to go on this journey where, well, got at least some of the biggest brains have to go solve bigger problems, and you need to create that infrastructure platform for these folks to make work on a big problem. I mean, there's nothing wrong in working on another TikTok. We need that too, but at least some slice of that big brain should also go and work on big problems.
Why now? You could have easily just ridden the AI wave, especially with your experience under the belt. You talked about perspectives changing. I know there's a personal story there, maybe a little bit, but why now?
Yeah, that would have been easier, isn't it? Raising. I mean, I just came from a fundraising process, and raising money with an AI company would have been easier, I think. But the three reasons for me. One is I worked on these computational problems for a long time, including AI, and I've realized I've got to. I mean, it's probably obvious, but I concluded that everything's becoming an energy problem. If you don't solve energy, our energy requirements are going to go just exponentially grow now. And if you don't solve energy, none of these problems will get solved. And I'm personally a big fan of solving these problems as a software engineer myself. And the only way you can solve them is with energy. And you need to solve energy in a sustainable, resilient fashion. Otherwise, we'll all end up either doing more damage or limiting human creativity as a civilization. None of them work. In fact, I think our progress as a civilization is completely directly correlated with the amount of resilient free energy that's available, energy abundance. And for a long time, we had that, and we still continue to have it. And the problem is we've looked at it as an abundance problem, as in like, well, let's just do whatever sources we have. Let's just make more energy possible. I think that has to change increasingly as we go forward with these 10x, 100x, 1000x energy requirements. You need to think of more of an energy resilience as opposed to abundance, where you want abundance, but with a system that works for the next, I don't know, 10,000 years, not just another 100 years. That's what the fossil fuels have enabled that. That's one which is more practical reason. The second reason is that we just discussed, where I got to a point personally in my career that, well, at least I gotta work on these big problems where something that means longer term, something that means has a larger impact. I also believe societal impact and business impact are never mutually exclusive. The only way you can actually bring in societal impact is via proper business impact. And I wanted to work on something that has that larger impact in its scope. The third one is actually a lot more personal, where when about the time when we started Fourier, was our second child was just born. Having little kids kind of changes your perspective on what you want to work on. And as going back to my first theme, that limiting human creativity is what's been nagging me. That's not how I want the future generations to be, especially not only my kids, but in general. We've been blessed, at least personally, I've been blessed, and our generations have been blessed that you could make that progress. And we want to do the same thing for the next generation. So that's probably the strongest motivation to some extent, but all three led me to thinking that energy is the problem that at least I should be spending the next few decades of my life on.
Yeah, no, that really resonates with me, and actually one of the motivations for me to launch this podcast. So, very much resonates with me. Your colleagues have unequivocally said that your first principles approach is your edge. And you being able to deconstruct a problem at its atomic level, in this case of hydrogen, quite literally, upwards, is where you have an advantage. So, talk to me about bringing that background and experience working in tech and AI, but taking that sort of speed of light innovation, applying that to something as boring as hydrogen.
Great. I mean, first I would disagree. Hydrogen is actually pretty exciting. We You should come visit our lab and we can show you how exciting it is. I think the first principles approach, as it is now made more famous by some of the companies, to me it came naturally. Again, going back to the engineering curiosity and roots, that's what an engineer is supposed to do. You have a big problem, you break it down into pieces, and you see if each problem can be tractable, solvable, and or you have alternatives. That's what we are trained as. Maybe that's how my brain works. So when I looked at energy, I'll start with energy first, and then we'll go to hydrogen. If you look at energy resilience as a thesis, there are fundamentally two problems. One is how do you make massive amounts of energy accessible or produce energy? I think you have renewables, you have probably fossil fuels will play a role in it, but nuclear will play a large role in it. All these problems are interesting. But then the second piece is also how do you, once you have these energy production efficiency solved, you need to be able to store it, and they go both hand in hand, because if you look at existing energy production systems, they didn't never needed long term storage. But when you talk about renewables, when you talk about nuclear, you need to store large amounts of power for long duration to be able to create that resilient system. When I looked at energy, those are the two problems for me. In fact, for a little while, we looked at like nuclear and how things are evolving there. But then more and more, we came to the conclusion that storage needs to be a piece that needs to be solved. And that's where I got very interested in medium storage. Again, within that bucket, you have batteries, which are great for short-term storage. Then you have medium to long-term storage. There are different solutions that people propose. There are different companies working on different ways to do it. But we thought hydrogen has fundamental qualities, which is round trip, clean cycle, that made sense to me. And again, then you look at, if it is so obvious and the chemistry is so uh, basic, it's just a basic high school chemistry that at the base of it, why isn't it a reality for a long time? Every other decade or so, people talk about hydrogen, then it never gets realized. And we were looking at, is there an inflection point now? And we'll probably talk a little bit later also on that theme. But at the end of the day, it boils down for me, again, with hydrogen, what are the problems? Again, how do you produce it efficiently, but also how do you distribute it? And distribution of hydrogen is a very, very hard problem, because the molecule, while energy dense, while easy to have a clean cycle, it's just super light. It's also super voluminous. So it's very hard to transport. And pretty much everyone else that we looked at solving times, they all assumed that, oh, we'll distribute hydrogen somehow. And we looked at it and we thought, well, that's not how we think hydrogen should be. It's always easy to move electrons and then add atoms. So why don't we just generate it locally wherever it's needed? So that's the final thesis that we came to. But it took a long time to understand that, especially also because it's a new market for me. It took a long time to understand various stakeholders, what the problems are. But if you take all that out, going back to first principles, the molecule makes sense for specific use cases like long-term storage, longer duration transportation. It's a nice fuel for various. We are not like fanatics where you want to apply hydrogen for everything. I don't think hydrogen is the right solution for every possible energy application, but it's kind of in that big suite of solutions that you need for energy transition. Hydrogen will play a large role, and that's kind of eventually how we got to. And part of it is also when you talk to people, you kind of form a team around it. A lot of things contribute to it. But at the end of the day, again, it goes back to let's go to the root of the problem and then try to solve it.
That's actually a great segue for us to talk about the political and economic volatility, if you want to call it that, or just differences in it at its most basic level. The global hydrogen scene is kind of messy. It seems like EU and Germany are doubling down, and they really firmly are backing these very large scale infrastructure projects. I know India has huge ambitions while there's tons of complexity there. And then China seems to continue to dominate this electrolyzer cost curve just because of the manufacturing. And so you've got like massive hydrogen farms, you've got the production inefficiencies you talked about, and then you've got the complexity around transportation logistics. I think General Catalyst calls this the market structure failure, not a molecular one, which is kind of what you were alluding to. And you at Fourier have seem to have flipped that script a little bit with what you said, the modularity of it, the rack size on site hydrogen blades that learn and deploy real time. So talk to me about, this notion of like centralized mega projects that are chasing policy to like figure out how do you leverage those tailwinds. And then you've got a fundamentally different approach where you're saying you've got this modular approach that sidesteps the policy game and will position you to go and win in regions that have wildly different, say, regulatory frameworks and power mixes.
Yeah, I think it's two separate answers that I would touch upon. One, at the end of the day, this is again having this startup mentality. You really want markets to determine your fate,
Yeah.
not politics. And that also goes back to the first principles approach, where it has to make sense from a business perspective. No amount of tailwinds from a government standpoint will change that. It'll help, but it won't change that. Let's take a higher level view on if you are a government or if you are public infrastructure trying to improve it. It makes sense from that perspective to do large projects because it's easy for the policy to invest or subsidize large projects. But from a hydrogen perspective, I don't think that centralized approach makes sense. What most people are trying to do is take that traditional fuel kind of mindset and apply that to hydrogen, which is fundamentally a very hard molecule to move. And we would actually take the other approach where electrification makes sense. You electrify everything, then you push hydrogen to the edge, where you don't need to transport the molecule, you only transport the bits and electrons, which to me physically makes sense. Having said that, there might be some cases where the centralized approach obviously makes sense. When you have large corpus of solar or renewables installed somewhere, it makes sense to co-locate it. But from a wide range of market applications perspective, I strongly believe that it's more distributed approach makes sense. Again, too much of public infrastructure involvement always tends to favor centralized systems like the grid and all that. But we never think that's how things should be. And with that, as you said, some of these existing plans are hitting that roadblock where those economics kind of really stopped the moment government funding falls off, or they realize that the physics of the problem doesn't really allow you to do it. So as extension of it, what we think at Fourier is hydrogen is still a critical piece in this environment in energy ecosystem. It's just being thought in a different way. And we think by making it modular, and we'll talk about modular in technical sense too, but that can be deployed at the edge, as close to the edge as possible. Whether it's a fueling station, whether it's a power backup, or whether it's a feedstock, you just remove transportation altogether, or at least minimize transportation is how you would solve hydrogen. It hasn't been possible until very recently because traditionally hydrogen plants are these massive either methane reformation plants or even these big alkaline or other forms of electrolyzer systems. It's only been possible recently that you can actually do it almost as if you deploy a data center or you deploy a refrigerator or other distributed things. And technically also that's probably why people haven't tried it. And third thing is the way to scale hardware. If you are a pure hardware infrastructure company, you would imagine that I would make the largest possible piece of hardware, and then that's how we would scale it. Time and again, that has been proved wrong. If you look at like IBM mainframes versus how PCs evolved, solar panels, where now you have these small panels versus huge panels that people used to make batteries. Every industry, you would think that if you're a very traditional hardware focused mindset, you would think that I'll make the biggest possible system. But the reality is, you would want to make the most replicable, smaller part that you can continue to replicate across different applications is the right way to scale hardware. And that also gives you this software defined hardware, which we'll talk in a bit. To summarize, I think the large projects will be a tailwind to some extent. Like you have countries like you said, India, Germany, all betting in hydrogen. The approach needs to be slightly different, where you push it to the edge, push it to microgrids, push it to the edge of consumption. At least that's the bet we're making, mainly because transportation of hydrogen is not tractable.
Yeah, I mean, I think this takes us to serve the innovation you're driving around your business model itself, which is what the sort of reimagination, if you will, of the market structure is in the context of hydrogen. And like you said, you've got large scale projects, say in a country like Germany, that's very much government backed. You've got massive like capacity announcements, yet not as many off takers because, again, they're just waiting for policy reformation and incentives, which is what makes it really hard. So let's talk about the the cost aspect of it, where the unit economics now makes a lot of sense. I think in your Series A announcement, you talked about the cost in the pilot projects that you're able to deliver is half of what is being paid today. So talk to us about one, what that is and how you actually get there.
For a long time, and it continues to be the case, where people are chasing this dollar a kilogram price target, which I think at a high level makes sense. The problem with chasing that milestone is it cannot be achieved today without public policy funding. And it all depends on the price of power and various other factors. I don't think that's the right approach to take, because it's just chasing a target that's always moving. The right approach to take it is, how do we actually make it practical from a technology perspective, and go with the highest price that people are paying for hydrogen today, and that's transported hydrogen. If you look at transported hydrogen across the globe, it people pay anywhere between $8 to $20 a kilogram. In the US, it's about $11 to $20 a kilogram, because the transportation of hydrogen is very expensive, versus production cost about $1.50 a kilogram. If you look at methane-based hydrogen production, that's intentionally we want to go after that end of the market. Also, fundamentally, we believe transportation is to be minimized. At that end of the market, we can be cheaper. We can be less than half the price. End price, we can deliver $5 to $7 a kilogram to the customer, and then still make margin on our end, save customers almost half the price. The advantage that gives us, it's also a medium, small niche end of the market. Like, if you look at the long tail of the market, which is why most other companies don't want to go. They want to go after these bigger projects that gives you $100 million contract day one. We're happy to go with this market because fundamentally it aligns with our vision of distributed on-demand hydrogen. It also has a price leverage that you can build. It requires a different solution to build from a technical standpoint, but it gives you a significant price leverage by just our pitch to these customers is simple. It's cheaper, which otherwise they won't even talk to us, because these companies are very old industries, have very thin margins, very thin bottom line, and we are like saying it's cheaper, then it's safer, and then it's cleaner, and then in that order they get excited. That's pretty much what, and it's a big market. It's hydrogen as a very large market as a commodity. So this is, even though it might feel small, and it's still like $25 to $40 billion just the transported hydrogen market in the US, in the world.
That's huge. I mean, it seems like, instead of the traditional startup mindset, let's go build it and then they'll come. You've actually focused on the demand side, where you've said, where are the existing customers, say industrial companies that are already paying a premium for transported hydrogen? And let's figure out what those use cases are and then start delivering value.
In many ways, that's what traditional startup mindset should be. In fact, when that's all, you first talk to customers, you make an MVP, and then you go deploy it, and then you incrementally go up above the ladder, which is what we do. We would do if you are a SaaS company or a software company, and which is what we should do for any company in some ways. In many ways, I feel like as a company, as a startup especially, you need to earn your right to work on harder and harder science. Again, I'm not an expert in it, but there's other companies which take the other approach where you go at the end, you try to solve science first, then you go down the market. I don't think, at least from my personal preference, and if I can say it, I think that's how companies should be built, where incrementally you earn your right to work on harder and harder problems by making an impact from day one. With that approach, you should absolutely go to the market that fits your thesis, and then find customers that fit your thesis. Oftentimes, you may not find customers that fit your thesis, then you kind of pivot. But if you actually keep finding customers that are in your thesis, then you just grow from there. So I think it's just a more, I think systems thinking in approaching it, but I don't think it's non-traditional. If anything, that's how startups are built normally.
Before we talk about like the technology aspects of this, around the business model innovation itself, what have been like your biggest, say, one or two observations where you felt like you had missed something or something was a surprise or learning in your last 3-year journey, I guess?
Yeah, I think one of the things that when we looked at this, and I started spending, I don't know, dozens of companies that we spent all over the world. I had to go to India, Indonesia, Europe. We went to these independent companies that use hydrogen in various use cases. We thought making it cleaner, making it cheaper, and it was their main one of the main selling points. But time and again, safety comes with a very high value, and this is something that I learned because I don't come from this industry. But if you make anything cheap, because these companies, for example, do in many cases toxic chemicals in their processes. They make all kinds of unsafe things in their campuses. But the thing that they're most concerned about is oftentimes the hydrogen tank that's sitting in their premises and the processes around hydrogen. And if you simplify it, or if you make it better, or if you make it safer, they are significantly more valuable to them. In fact, in many cases, they can't even quantify it in dollar value, but they even care more about it. Even if you think that you ask them to pay more per kilogram, if it is safer, they will be. So the safety aspect is something that I very early learned to be a big lesson for me. And obviously now with Fourier, everything we do is like safety number one. But we're also by nature, by technology, we are just significantly safer than having this transported infrastructure by moving it on site. So the safety value prop is kind of opened my mind in some ways. But other than that, the main thesis around transportation of hydrogen being not only expensive but clunky is interesting, and it's reinforced. The second learning was, because hydrogen transportation is a very hard problem, or distribution of hydrogen is a very hard problem, there are only 2 or 3 companies that do it really well, or do it really. There's no, I mean, it's not. It requires a significant amount of capital investment, all with like very small margin at the end that you make. So there are only few industrial gas giants that actually do it. As a result, the customers of hydrogen, or the companies that buy hydrogen, have no leverage, because they're all limited by 2 or 3 suppliers, and there's no price leverage that they have. In fact, the suppliers have all the leverage because there are only a couple of them, and there's usually market dominance. So the price varies, and it's not based on customer demand; it's based on what the suppliers decide to price it at. And these customers don't like it. They don't like the price volatility. They don't like that they don't have control on price. They don't have bidding power on the leverage on the price. And by making it distributed, you actually make the level that ground where they can control the price. It's just at the end of the day, you just have price of power as your feedstock. So that's another revelation, I think, for me, where how this industry is structured. You just have
Interesting.
2 or 3 suppliers.
Yeah.
Pretty much.
And as you think about continuing to scale, I mean, like you said, the transported hydrogen market, it's in of itself is 25 to 40 billion. So there's a lot of things that need to be solved there. But as you think about either expanding to other use cases or other industries, or within that broader segment expanding, what do you anticipate to be kind of the biggest barriers around the business model itself?
Obviously, the main problem that we are trying to solve is power storage, power backup.
Yeah.
This market is a way for us to prove that transportation of hydrogen is it can be solved or can be avoided. The way Fourier would expand is by providing this safe, clean uh, power backup solution that works in adjunct with batteries, where you provide the long-term power storage. So that's where we would grow. I don't think we would just be in this chemicals industry space. So if that's a very different. I mean, the technology is very similar. The use case is quite different. Where at that point you're not looking at price per kilogram. At that point you're looking at round trip price per kilowatt hour that you're storing, and how long it is basically levelized cost of storage is what you're looking at. It's more of capex reduction, and then you're also looking at how long the device can run, how much power you can store, among other factors. So even then, you're not chasing this wild pipe dream of dollars per kilogram target. You're chasing, can I be better than a pure battery solution? Can I be better than a diesel genset, for example? That market also has you need to, obviously, these companies don't, like, if you look at a data center, for example, they don't use hydrogen today as a backup.
Yeah.
At that point, the barrier, I don't know if it's barrier because economics work out. You just need to build this black box solution that you just say, this is your battery, connect it. It provides you around the clock power, both as a UPS, both as a power backup, and give them. So it's less about, oh, it's hydrogen or anything else. You just give them a solution that just works. And I mean, that's where we will go. And it's less about convincing people to use a new technology at that point. It's more like, hey, you need a power backup. This is a better power backup. Let's go build it. The reason I don't think that should be our beachhead is, number one, because this is the other market which is there, price leverage. You go with that, and you need to hit a certain scale to go into a market that's relatively early right now.
Yeah. I want to come back to that storage conversation because there's a lot of, I think, the technical aspects also that help solve for it. But let's dive deep into sort of this technology innovation part where you've essentially taken the principles of building, say, a data center, and taken that and applied that to an industrial physical infrastructure, energy infrastructure problem like hydrogen. Walk us through, just purely from a hardware architecture perspective, and then what you call the software defined infrastructure. How does help us like visualize that?
I think the main difference, probably mainly because I don't come from this electrochemical world, uh, people think, and most incumbents still do that, is let's make the largest possible stack that can be made. If you look at hydrogen production, the modern electrolysis is done in these thin layers of cells, which are porous membrane with catalysts coated on both sides. Catalysts are metals. You pass current across it. Water breaks down, and the hydrogen production rate is directly proportional to total surface area or active surface area of your cell. So you want to produce more hydrogen, you need to have more surface area, make larger and larger cells. Well, it's not physically possible to make an infinitely large cell, so they stack them up together, and still they want to make the biggest possible stack.
Mm-hmm.
The problem is you cannot obviously make an infinitely large stack. At some point, you still have to modularize it. People assume that we'll do it at 10 megawatts or 1 megawatt or 100 megawatts. Again, these are huge equipment that people build, and if you're only making one of them, yeah, that's the cheapest way to make it. Again, like I said, that this typical hardware mindset. And when we looked at it, and they also spend a lot of research and development time on scaling up these stacks to become bigger and bigger while keeping the efficiency of a small stack. We thought about it and we looked and we thought, well, all that complex scaling up, why go through that? Let's start with a small stack, which can be run at higher. In fact, our stacks are run at way higher current density than traditional stacks, and then stop there, but push the complexity of running the overall system efficiently into a systems engineering / software problem. So if you look at batteries, for example, the same thing. They use a lot of tiny cells and create a stack of it, and then they have this system called a BMS system that's equivalent to run the overall system into thermal efficiency and operational efficiency, all controlled in software. We are taking, I would say, an analogous approach to that, and obviously that software-defined architecture allows us to run these stacks in various different scenarios at their peak efficiency. So to summarize it, if you look at hydrogen production, there's two. One is electrochemical efficiency, which is how much catalyst do you do, what kind of catalyst you use, what kind of coatings you would use. And then there's operational efficiency. How do you run, given a given cell, how do you run it? And that determines the overall efficiency, but also lifetime of that particular stack or cell. The electrochemical efficiency, I think, is largely solved, at least in the proton exchange membranes or the modern electrolysis cells. Where it's lacking is operational efficiency. Most companies want to do one big stack, connect it, run it, and then not much after that. We think there's a lot to do in the operational side, and that's where we are coming in. It's again taking the battery analogy. You would still have cells like Panasonic making cells.
Yeah.
Then you have companies like Tesla making battery packs and battery systems. We are kind of analogous to that latter part, where we think operationally these stacks, how you run them, doesn't matter. You make the most electrochemically efficient cell and stack architecture. If you run it the way it's not supposed to be run, you will not get as much efficiency, not get as much lifetime from it. So there's no point in building a Ferrari if you don't have the right driver. So it's kind of similar, and we want to define that. We want to simplify the hardware, make a lot of them, and a replicable hardware. And then our system looks at both intrinsic variables like temperature, pressure, IV curves on each stack, and then optimizes given a power input, given a hydrogen output that we're producing, just overlays the power on a number of stacks to not only optimize lifetime but also optimize efficiency over time. So this is a slight, I wouldn't say it's a fundamentally different approach. It's like you alluded, it has been done in many other industries. It's newer for hydrogen. Again, even within hydrogen, we're not probably the only company doing it that way, but we're probably a rare set of companies that is doing that way.
Yeah, so it's interesting. It sounds like it's the analogy around Tesla's compute layer, and then you're essentially invoking a controlled systems type mechanism. And you've got in your architecture, you've got the data-driven optimization perhaps, and more of that operational intelligence insight into that.
It's a software hardware loop, which is very important, where you design a stack and it generates, and we collect that data. It generates a ton of data when you operate it. And that data in turn affects your algorithm that runs that stack. And that algorithm kind of determines the performance of the stack. And then you go improve it, you upgrade the hardware. Then you have a loop between your software and hardware. It allows us to iterate on these stacks much faster both from a software and hardware perspective. It's that positive loop, that learning loop that you create is very important. That's how we actually make progress on these stacks much faster. We can also, because we have an array of small stacks, we make an improvement, we swap it out, we put it in, we run it with the rest of the system, and then we know what metrics that we're looking for. It also allows us to experiment, because traditionally these things are done in complex models, simulations that people do, and it's very hard to simulate everything. We can actually, we simulate, we have models, but we can also put it in real time and then run a real time, test it, and then make progress as hardware. So that's the second part. And also we can also do this predictive maintenance, which is basically even before a stack or a cell could potentially go wrong, we will know because we're constantly getting a ton of data, compare it with other similar stacks, and we can actually go predictively manage it, not wait until it breaks. In fact, if you have a one large stack with one cell broken, you just don't have a choice. You have to replace the whole stack, take it back to your factory, and that limits your redundancy. Like for many customers, let's say they want a megawatt capacity, they would deploy a couple of megawatts, but just for redundancy, because that's how their stacks work. We can actually reduce that. We can even give the same amount of redundancy with just 1.1 or 1.2 megawatts, because we have a lot of small components. So the redundancy, in a way, the cost is down, because instead of deploying two systems, you're only deploying one system or a little more than that. So there's many benefits of modularity. Again, modularity is not new, but it's new to this domain, I think.
Yeah, so you alluded to this earlier, which is now you're able to actually go make modularity a reality in hydrogen. What is that technology? Is it a technology unlock? Is it something else? Or is it just the, again, systems level approach?
I think it's a systems engineering unlock. Again, depending on what you call as technology, so it's all technology. We are not fundamentally an electrochemistry research company. We're not trying to invent new catalysts day one, although we have our own stack architecture. But we are more of a systems layer, where what is given a particular electrochemistry, what is the best way you can build a system around it? How do you operate it? So the unlock here is more around the systems engineering of it. Having said that, that unlock happened because these cells now can be made smaller, can be run at higher densities, can be performed. I mean, it wouldn't have been possible 20 years ago. This is just how it is with the control system that we have. So the technical unlock here is to reduce the hydrogen production problem into its smallest possible blade module, and then replicate it. And it also be unlocked in a different way. If you look at hydrogen electrolyzer system, yes, the stack, the electrochemistry part of it is important, which is basically takes water power, converts that water into hydrogen at a cellular level. But equally important, or probably almost 20 to 30% of the cost of the system, is also the power systems that run these stacks. You have an input high voltage AC power that's coming in, and you need to convert into low voltage DC and run these stacks. These power supplies are oftentimes custom built. Most of these companies actually built these power supplies from scratch, because if you're building a 10 megawatt stack, you need a 10 megawatt power supply, you need to build it. And power supplies are, it's almost like these analog devices, which are a very linear power price path. So it's dollars per kilowatt. And of all these companies, on average, like $200 a kilowatt, roughly is what they're measuring against. The interesting part is power supplies is often a big dip in certain points. It's a linear curve from a price perspective, but at some specific sizes there are dips. The reason that dips exist is, for example, a server uses a power supply, and at that size, there's a big dip because those units are sold in like tens of billions of units or some insane amount per year. Again, you'll have battery systems have a priority. I mean, all the way at the low level, you have Apple power charger, power supply. Those will be like very cheap, and that's the economies of scale of the market. We kind of ride that. We match our blade sizes to that's the data center analogy. Even going deeper, we actually use off the shelf power supplies and then reprogram and redesign them a little bit to run electrolysis. So that way you can actually ride that, and also you get these super robust, super high quality power supplies that are already being sold in other industry that you can use it, and then you can actually create that software layer.
Yeah.
So that is another unlock
that's really clever, because now you're not, you're not investing in building this power infrastructure that's custom made, and anything around data centers now is commoditized. Of course, the supply chain challenges come in when you've got, kind of the geopolitical scenarios that are unraveling at the moment. But in general, you've got something you're building out of commodity components that are produced in tens of billions.
There are many. I mean, yes, that's the. It's architecturally it makes sense. For example, if you use a 48 volts railing,
Yeah.
that's what like data centers, that's what like Tesla is proposing for their cars. All of a sudden, you have these ton of components that are already built for that architecture.
That's right.
That you can just leverage, and then not like you can just plug them in as it is. You still need to do engineering to make it work. There's so if you look at other industries,
Yeah.
and this is another piece which goes back to our first high level point where you need that interdisciplinary thinking around this.
Yeah.
This is what's been missing if you look at this industry to begin with. You bring in these other ideas from other industries, and then say, okay, let's build it for a standard as opposed to custom building everything and then you make it work. You unlock these economies of scale. It also gives you the opportunity to make it more and more software defined, because most of these components generate data. Most of these components actually allow you to do very cool stuff with in terms of programmability of these things. So yeah, I can go on this quite deeply in terms of voltage architectures the whole power architecture is an unlock from our side, along with the stacks.
Yeah, that's amazing. So when you think about like scaling to say 10 years out or maybe 5 years out for Fourier, and you've got like do you think of it as millions of these micro electrolyzers that are in a blade, and somehow there's, software that's stitching it all together? Or is it a different approach that allows you to either compete with or get as close to the gigawatt scale, if you even want to go in that direction?
We can build a gigawatt scale system with the same architecture, no problem. Again, not to beat the Tesla analogy too much, if you look at Tesla Megapack, they're similar architecture. They start with batteries and then they scale it up to build 100 megawatt systems with the same. So there's no limit to scalability of our system. Again, going to data center analogy again, you can build any capacity, all with those small blades, server blades. So scale is not, in fact, what we're building is for scale. The way our system works is you have these independent modules, we call them blades, because I come from the data center world, and then scale it up, and then this one software that controls no matter whether you have 10 blades or whether you have 1,000 blades in a specific, or even 1,000,000 blades in any specific installation. It'll just scale all in nice one software defined layer. So we can go build a large gigawatt solar power storage system with the same architecture that just cascades things, and that's the bet. That's not, like you said, 10 years. That's the horizon. We don't want to customize anything to a specific size. That's the main difference, and then you can scale this up to any size. And so, yeah, I would absolutely think that we would build these various for each different use case, like a fueling station or an airport which needs hydrogen for fuel, or a shipyard, or a power backup, a data center that needs a power backup, or some microgrid or semi-large grid scale power storage, all the way from a small chemical factory using hydrogen at, I don't know, a megawatt. We would build the same solution that scales across these applications. And the idea is we would make one blade architecture that works for all of them. Or it could be your home power backup at some point.
So it's more about where does the economic make sense, right? Like, where do you have
That's right.
economic viability for what application or what use case at what point?
Yeah, and also economic viability comes with scale.
Yeah.
Right.
Yeah.
If someone asked 15 years ago if EVs would make economic sense, you wouldn't say yes, because it wouldn't make sense at that point. It took few companies forcing themselves. So sometimes it takes some bold vision and maybe some craziness, or almost naivety to go through it. But economics are a function of scale. That's the bottom line. I think I actually look at it as, does it make sense from a technical standpoint? Does it even make sense given various comparables? And then you need to go make it happen. And then it's a business approach to it. What market do you attack at what time is very important, because day one, if I say I want to go to airports and then build a fueling solution, I think that from a technological standpoint that works with hydrogen. But from a business standpoint, it's just a very hard market to crack. In fact, one of our investors is Airbus Ventures, who believe that this is a viable path. But that is not the market that I would start. So, from a technical standpoint, it has to make sense. But the approach you take, the scale you get to before you solve a problem, will actually control the economical sense, I think.
So it's, you've got the technology innovation you're driving, and then you've got not just a distribution, I don't mean distribution in the context of hydrogen transportation, but I mean it in the context of like bringing your solution to the market, your go-to-market approach, and how you time it and why you time it, what regions you're attacking, right? What industries. Interesting.
Right. I think it's equally important as a startup. You need to have both, and that's how you kind of solve the problem, I think.
Václav Smil has called hydrogen an energy trap. He's, I think, cited that there's 60 to 70% loss of energy round trip, electricity to hydrogen and back. And yet you've got, EU and Germany and even actually International Energy Agency betting on hydrogen as a storage solution because batteries cannot solve for the multi-month duration or, say, extreme climate variants. How do you think about hydrogen? You've talked a little bit about that, of course, but would love to maybe dive deeper on that.
Yeah, I think few people have claimed that, I mean, some of those people are actually famously proponents of first principles, but they often miss a fundamental point where, yes, the efficiency cycle is important, but there are three different. At the end of the day, it's a cost, right? That's what matters. Most storage solutions, including batteries, are all priced per storage density, as I would like call it. It's like dollars per kilowatt hour. The more you store it, the more you pay for it. It's linear on the amount of storage. It's like batteries, for example. If you want to store for 1 hour versus 2 hours, it's double the price. Hydrogen, on the other hand, is probably one of the few solutions that is actually priced per power density. So you're actually paying upfront for all the power, the kilowatts that you wanna generate, but then storage incrementally becomes cheaper and cheaper because you're just adding more storage, like more tanks. The tanks are expensive, but nothing compared to the power. So the average dollars per kilowatt hour, it's for a large system for hydrogen, is significantly cheaper compared to many solutions. There are a few other solutions which are probably more economic, like pumped hydro would be interesting, but that can only be done in certain geographical locations. You cannot be done in anywhere. But other than that, if you look at pure cost per storage, eventually, I don't think any solution comes close to hydrogen as a price. That matters for efficiency. It's if you look at only 100% or 90% efficiency, and that's your only metric, I think it defeats the purpose of looking at the problem holistically. And I mean, it's amazing how sometimes experts make these like simple mistakes to some extent. Having said that, like I initially also said, hydrogen is not the solution for everything, right? If you have a car, for example, you can charge it overnight. You don't care how heavy the car is. Yeah, then batteries work, and it's only short term. Picks out. If you're looking at an hour or two of storage, batteries are great. But there are other economics that dictate the long term power storage. So in that sense, anything above 4 hours today, lithium ion would be a bad solution for larger amounts of power storage. Anything above 12 hours, it's very clear, or anything about 24 hours, it's very clear the hydrogen will have a very clear one. It's actually between that 4 to 12-hour gap, you would think of whether hydrogen is interesting or not. And then that all depends on the scale of the production and capex improvement that you can make, all that. But at the end of the day, I can even show you math that even a classical home battery solution would not pay off over time as a hydrogen solution at that scale. Again, we're not trying to build home power solutions at all, but it's just the economics of it. Even if you include a round trip efficiency of 50% for hydrogen and a 95% efficiency for batteries, it still does not work. I mean, we've used gasoline engines for 100 years.
Yeah.
They're what, 25% efficient? It's not just that number that you should look at. You should look at the overall economics of it. I think that's the first problem with experts talking about it. But for industrial use cases, I think it also makes a lot of sense. The way we look at power storage, power backup as a solution, you will probably have a battery first layer for 1 or 2 hours of round trip, like a cache, and then you have a larger cache with something like hydrogen, which will work in conjunction with the batteries to create an overall solution. In fact, it's also it could be potentially that you would remove the batteries altogether, but I can totally build a solution. Think of a solution where you'll have long term storage and a couple of hours round trip solution all together that runs as a storage. In fact, if you look at hydrogen as a power backup, I mean this is a wild scenario because, like I said, we're not building a home scenario, but let's talk about it. If you think of a solution where you have a hydrogen power backup, if the bulk of the efficiency is going out as heat in water, so you could actually use some of the water as hot water. So you actually then it becomes significantly more expensive. You can also use some of the hydrogen in your natural gas pipelines, and you don't have to change your appliances. There's a solution to be built there. Again, it's always debated until someone builds it.
Yeah.
And again, I go back to, does it make sense from a base principles perspective? And I think it does. Again, it all boils again to how do you crack that market? How do you target that market? But there's nothing fundamentally wrong in the molecule that again, otherwise, like you said, there's a lot of experts also invest in hydrogen for the same reasons. Your other question around why EU and other countries are doing it. If you take an example of India, India does not have any local natural gas or fossil fuel bases. They have a little bit, but they're fundamentally relying on other countries, so they don't have energy independence in some ways. What we have there is a lot of solar, a lot of scope potential for solar, wind, and other renewables. Then how are you going to store it? The only way India thinks it can bring in energy independence, energy resilience, if you want to use that term, is hydrogen has a big role to play in it. So there are certain geographies in the world where Germany is another example. Again, it's not, if you look at only round trip efficiency, it's just, you miss the point.
One parameter.
But this is just how you cannot think of a solution where you're going to deploy batteries for multi-day, multi-month storage. There are other solutions to complete it. There are other solutions people are working on. Long-term power storage is a big problem that a lot of startups have worked on, a lot of big companies work on. There are various different solutions that are being proposed. But fundamentally, the hydrogen, the main reason hydrogen will work is because of this power density versus storage density problem, I think. Because it's just priced. The longer you want to store, hydrogen is just will become the cheapest solution eventually, barring a couple. Maybe, like I said, pump hydro, compressed air comes close. They all have their own issues.
Interesting. So what would need to happen in the next, say, 2 or 3 years, not just for Fourier, but in general, for this to be ubiquitous? Is it policy reform? Is it more commitment from a capital perspective? I mean, the answer could be all of the above. But if you were to say, like, the most critical things that need to happen over the next few years, say 2 or 3 years, what would those be?
I think I'll again go back to supply and demand. The amount of renewable energy corpus that we will have globally will continue to increase, and it has to continue to increase. There is no second way about it. It's actually the cheapest way to produce new energy now. Even if you include natural gas, coal plants, everything, it's still by far the cheapest way to produce energy. So there will be an exponential growth on how much renewable energy that we would have. I'm actually going to put nuclear also in that bucket. And that will happen. Doesn't matter what the public policy tailwinds are. I mean, they did help that in the beginning, but now it's on a trajectory that's growing, right? Doesn't matter. Even even today, even in the US, the fastest growing energy production system is in renewables, and it undoubtedly keeps growing. And the moment that grows, you need to have a way to store it. There's no other way. The other side of it is the demand part of it, which is not been. I mean, until now, electrification was the only driving demand for power, which is like EVs and other things. But now you have these amazing applications of AI that we're talking about, all are powered with, again, tens of hundreds of times of what energy consumption. I mean, average data center used to be what, 2 megawatts? Now they're talking about a gigawatt data centers. So all these things are need to be powered. And again, these companies are now talking about local nuclear plants or local renewables, or they just don't have power. And that will continue to happen. Once these two happen, it's inevitable that you need to hit a certain storage capacity. But where we think, I think that it needs to be different is people still talk about this. Oh, let's create these large multi-gigawatt storage at grid scale and then solve the problem. I don't think that'll work. You need still distributed, just like they're talking about on-site distributed nuclear, for example. As wild as it could have sounded 10 years ago, now people are actually investing. People are actually putting them together. I'm sure your old employer AWS is probably looking into it for that matter. We're looking at distributed models of this, and then you need to distribute it. You need the distributed power backup, and that it's bound to happen. This continued investment is largely market driven. I think there will be regulations and public policy push around it, but I think the fundamental motion that will happen is around the just pure market demand. The second theme is more public policy around this energy resilience. Because the way geopolitics are working around right now, every geography is trying to protect its own or create its own self-sufficient energy, and it becomes almost a security existential thing for almost all governments. Like US is very much into it. We just spoke about India, Europe. Every country realized that they need to have an independent energy ecosystem, and for that, again, some countries can and have natural gas and coal and other resources. Some countries just don't, and they again need to invest in these things. It's again, it's not but because anyone wants to do anybody any favors. It just, in fact, this geopolitics, ironically, will actually catapult climate energy investments, because every country would want to have its own, every geography would want to have its own resilience, and that global energy resilience will also drive this. Again, those are macros, and if you look at it at the bottom level, you need storage, and I think there'll be a lot. I mean, energy storage. None of these are one solution that works for all. There'll be a suite of solutions, and I think hydrogen will play a large role in it. But these problems they take time. They're not your, oh, like tomorrow, next year, we'll just solve it. As much as the government would want to solve it, they have to maybe take a slower approach and let markets figure it out.
Yeah. What are 2 or 3 things that worry you the most as you're thinking about continuing to grow Fourier? What keeps you up at night?
What we're working on is a global problem. It's energy for everybody, energy for where it's needed, energy resilience. And as much as I would like to believe that it's a global problem you're solving, there's also this localized resilience that we just spoke about. Depending on how it pans out, uh, the optics of it, somehow people assume that, oh, because we are focused on this now, maybe this is not an important problem. That is to some extent worrisome. Because, like I said, ultimately markets should determine the fate of these companies, not necessarily public sentiment. So I intentionally and very carefully, I want to steer the company around technology, market, whether it makes sense or not, and stay away from this noise as much as possible, because we know the problem exists. We know the problem has to be solved. We know the demand exists, and that's all matters. But that, but the macro elements of it also affect your ability to raise capital, your ability to just in general get the word out. I mean, I won't say I'm losing my sleep on it, but it is sometimes interesting that we just tend to paint everything into with one brush. But it is, in fact, the way I see it, if anything, that localized independence, resilience that we are going after now will actually create more demand for a solution like ours. The other one is around many of the hydrogen use cases that we just discussed. It needs an ecosystem to be solved. It's not just that, oh, you have a hydrogen and then, because, for example, if you look at fuel, you need, I think hydrogen will be a great solution for a maritime fuel, whether it's hydrogen as a direct fuel or ammonia or SAFs. It's just, they're all carriers of hydrogen. But a ship, if you want to look decarbonize shipping, hydrogen is a great solution for it. But it's not just one company; it's an ecosystem, right? The shipping companies, the fueling companies, the ship manufacturers, etc. So for many of these use cases, the ecosystems have to be built, and successful companies, as they scale, can build these ecosystems. If you look at companies that we talked about, like the data center company like Google's or Amazon's or even Tesla's of the world, they were very successful in building the ecosystems.
Yep.
Like all the way from charging stations to now they're talking about diners. And if you look at Google, it's not just building a website, this is an ecosystem that built. And Amazon similarly. We have an opportunity to do it, but also at some point we'll be constrained if those ecosystems are not built. So I'm very conscious and very eager and bullish to the point where, well, how do we catapult that ecosystem? So it's also how do we bring together all these stakeholders, including other companies, including bigger companies, smaller companies, including governments at some point, to create those ecosystems is an interesting problem. Again, hopefully we'll hit a scale and then we'll be able to do that. But that's in the long run. That's how I would say would keep me awake at some point. But also that determines whether Fourier is going to be this gigantic scope versus maybe a smaller few $1 billion company. It depends on how successful we are in building this ecosystem.
Yeah, it's interesting because reimagination of the markets, like you said, requires you to bring a lot of stakeholders along and sort of like figure out, because each one of those stakeholders will have different metrics and different incentives. And so the complexity you were talking about, the shipping industry and the sustainable shipping, the complexity around that is just massive, right? Because usually either they're not talking to each other, but usually it's also misalignment. And maybe sometimes the incentives are like directly in misalignment with each other, right? Quite fundamentally, even. So, yeah, that's a really interesting problem. And if we were to continue to sort of borrow from that analogy from Tesla, like you said, or looking at Amazon from an e-commerce lens, I do believe that that is actually one of the biggest unlocks, not just for hydrogen, arguably for most of these renewable energy systems. And it goes back to how much capital investment you get, how much market demand you get. You talked about nuclear for, Amazon and Meta and Google have made huge commitments, right? So what is sort of that inflection point in the hydrogen story? Maybe it's around storage, maybe it's other aspects, but that's where I'm super excited to see how Fourier continues to, break new ground and really innovate across all the different dimensions. All right. So as we sort of spend the next few minutes wrapping this up, I want to come back to the theme around the transition or pivot from bits to atoms, software tech meets sort of physical infrastructure. As you reminded me, hydrogen is not boring, but some may say so. Okay, maybe let's start with your story and how you were able to convince investors and, say, employees, the first few employees you got on board, selling someone on you building another AI startup, especially having been a serial entrepreneur, is very different than saying, I'm going to go do something in hydrogen. How did that conversation go?
Yeah, there's multiple themes there. I'll unpack. Well, I'll start with a personal standpoint.
Yeah.
I can understand why, from an outsider's perspective, it seems like a big transition. But in my head, this is all an engineering problem, and also, yeah, I'm a software engineer. I think that way, but the way we're approaching it is, yes, we make hydrogen. That's the end product. Our whole architecture is defined in software. The way that's because that's for good or bad. That's how I understand problems. So I look at a problem, let's say hydrogen production. We want to convert immediately into how do I look at it from a software perspective. Everything we start with a simulated model. We start with no hardware. We start with all software pieces of the hardware. Then we build on top of it. Then when we build a piece of hardware, we'll actually virtualize it first. Then we can run tests. So everything is the approach is very different. If you really look under the hood of our architecture, uh, because that's how I am thinking. It's probably largely driven by, well, I only understand this problem that way. Let's actually convert everything into a data and algorithm. Then we'll just build hardware on top of it. So with that in my head, I don't think it's any different from me than a video compression or a camera. It's all feels like a software problem to me. Going back to your bits,
Yep.
yeah, we produce atoms, but in my head I see it as code. So it's for me, it doesn't feel like that big of a transition purely from an engineering perspective. The transition is around this interdisciplinary team that you need to build.
Yeah.
From going with, again, our last company was a hardware company, but it's more like building a team of mechanical engineers, thermal engineers, electrochemical engineers, electrical power electronics engineers, and software engineers all together working on this problem is actually a pretty interesting transition for me. That part is different because I've for a long time I would know every single piece in the companies that we build. Now I have to like have this interdisciplinary team where everyone has their own expertise and they all work together. So transition to your second theme, that is how do you convince people. First step is convincing yourself that it's an important problem to be solved, and it is not only important problem to be solved, it's actually a cool, interesting problem to be solved, and why it is gigantic in its scope, why it is. So that's the first part, convincing yourself. And then second part is convincing yourself that there is a path towards that.
Yeah.
I think if you can convince yourself sufficiently, then you can tell that story to someone else to be able to convince them. It's actually, I found for this company, it's significantly easier for me to attract top talent than, for example, some of my previous startups. It's because number one, it starts with how much I am convinced on the problem, and also it gives people a certain direction to work towards, as opposed to just being, oh, this is a cool problem. Absolutely, what we're working is a very cool problem, probably the coolest problem that I've ever worked on. I worked on some pretty interesting problems, but that's not good enough. I found that why you're working on it, and that authenticity of why you're working on it, and the kind of impact that you can bring is actually a very strong wedge in attracting those people, and you can actually create that very different interdimensional people team, and the only thing that's tying up together is that why.
Yeah.
And I think oftentimes an early stage company, or probably any company to some extent, the most important question is why.
Yeah.
What is okay, how is important, when is important, but all those things change.
Sure.
And it's all those things become hard at some point. But if you have a very strong why, which shouldn't change, then people can rally behind. And this is something I learned over time in my startups. Often in the first company, we would have probably many days where we would say, oh gosh, this is it. Tomorrow we run out of money. This company is done. We'll go for a walk, come back, something comes out, some solution comes out to just last another week, just last another day in some cases. And then things evolve. And that happens only because you know in your head why you're on it. I mean, it could be the team you're working with, it could be the person you're working with, it could be the mission that you're working with. These are hard. These are hard problems. Startups are hard. So that, because I've been very clear on why. And in fact, again, this is my fourth startup. I've never been this clear on why I want to work on a company. Again, every company felt very important to me, but I can 100% confidently say that I've never been this clear on why I want to work on a certain problem as much as I am right now, and that makes it easier for other people to join. And also self-selection happens at that point where people who don't believe in it, they don't join you. It's just very simple. You don't need to convince anyone. Just tell your story. And then again, building a team in a startup is always hard, especially as an early stage company. You don't get to pay as much as the bigger companies. The stock goes up in a bigger company. It's always harder to hire. Stock goes down. It becomes easier. But the reality is, at least there is a reason why people want. So that I think we continue to build a very strong team around that mission, convincing people. I mean, and then investors. I took a very traditional and non-traditional approach to it. When I started this company, when I was initially thinking about this problem, I thought this is a crazy enough domain and a weird idea or a crazy idea that no one will fund it, to be honest. And I even thought, well, someone might come and fund it, but then they'll take me in a direction that I don't want to go. I was 100% prepared to bootstrap it. I thought, well, it'll take me X million dollars to
Sure.
get to a state where we prove commercially, and then we go raise money. And I thought, okay, I'm crazy enough that I like I said, I'm very clear on why I want to work on it.
Sure.
So I'll have to put my my money also behind it. So I'll bootstrap it. That was my thinking. And again, just as a side note, as any entrepreneur, uh, the last thing you want is invest in your own company too much. It's just misaligns expectations. But that aside, I was going to do it because I was like prepared, and I also especially didn't want to get too much of climate focused funds involved day one, because I thought that's not our focus. Our focus is actually solving a business, solving an interesting problem. So from an investor perspective, I thought if we're going to have investors, we should have more generalist investors who are just thinking about it as a business, as opposed to like have that. I mean, we can have a mix, but those were the two things I had in mind. I just happened to meet Hemant from GC almost very coincidentally. That's a whole story by itself. How we met, and both of us kind of convinced each other that we needed each other in some ways. Again, he's a big time investor. Not that he would need me, but he had very similar ideas around this vision, and we kind of gelled. I even told him at that point, remember, that I don't need the money right now. I mean, if anything, I would need a relationship. And that triggered that investment. I mean, oftentimes it's funny because you probably, the easiest way to raise money is when you're not looking for it.
Yeah.
And that kind of happened for our first round, and it just again, I was worried that having a big time investor would derail potentially our vision. But we've been largely very lucky to have such a good fund back us in a way where they believe in the long term vision, and they believe in us to go through the vision that we have.
And then you got Airbus mentors on board.
Yeah, and then the second round is then you're like, it's beyond a story anymore. You have to prove your point. We did successful pilots. We had a track. It's not that easy raising money right now unless you are like you said, a deep AI company. You just need to call yourself a deep AI company. You don't need to do anything deep AI, but that would make it easy. But it's not it. And especially we raise money, we close around in February, which is, I mean, it's very hard. The only reason we were able to do it is because of all the things that we discussed. We have a very clear path on commercialization, and also a proven track record. When GC has been on the board, and they've seen us path, they've seen a path that we're going after. And again, we have our lead investors, Paramark and GC, both are generalist investors. We're not essentially looking at climate-focused investors. In fact, we've largely stayed away from it. But then we also have some impact funds. Airbus Ventures joined in because they believe in this vision. So raising money is always hard, like it should be.
Yeah.
Unless you ride a certain wave, sometimes it happens.
Yeah.
At least, unfortunately for me, I've never been on that wave. We did an AI company, deep AI company, before deep AI was famous. We were able to raise money.
Sure.
So I think raising money should be hard. And I personally never enjoyed raising money. As an entrepreneur, I belong in the lab. That's where I belong. But we were just lucky, I would say, to be in the right spot, to meet the right investors in the right time. But I think our approach to it resonated with a very typical VC mentality where you're not affected by the public policy waves. You're not affected by. You're not betting yourself on government subsidies. You just have a business that is cheaper. You just have a vision that makes sense, and that's probably why we got the support that we have. But raising money is always, if I had a formula, that would be raising money is never easy. It's also not enjoyable to some extent.
And talent is the other part of it, which you talked about, which is, if you've got strong alignment around the mission, then all of a sudden that becomes relatively easy because you also want mission driven people
Yes,
on the team.
relatively easy, and also you need to build a strong culture. But I think increasingly, uh, we need those different class of people, different dimensions people to solve big problems. I think I go back to my first point where the whole point of Fourier is, yes, there's energy transition energy resilience we're working on. That's a problem we're working on. And the whole point is to create a platform for people, like the brightest people that we meet, to go after the big problems, at least some of it. I think fundamentally over the last decade and a half or so, I think especially in the Valley, a lot of people are working on small problems, I think, and that has to change. And increasingly, that's what I saw missing. Again, this is more maybe of a personal reflection on my own, where I felt like, well, we need to work on bigger problems. We need to work on problems that matter. And it almost, I'm glad to see that at least some people are just coming out and say, okay, let's go after. It doesn't matter. It doesn't have to be in the space that we are in. It could be anything. But people here, especially the beauty of this area is people were not afraid of taking on huge challenges. I come from, for example, company like Google, where they, at the early stages of Google at least,
Sure.
they weren't afraid of going after any problem. If you take that example, Google built their own router.
Yeah.
Which company does that? There's
Yeah.
nothing to do with their fund. They just saw an engineering problem,
Yeah.
went after it. I think that culture has been missing to some extent in the last decade or so, with all these availability of free capital in some ways. So I think it's almost like at Fourier is almost. I hope it becomes that beacon for people to just say, let's just go back to solving cool problems that matter with an engineering math.
Yeah, I mean, you've said that Fourier was founded on the principle of engineering audacity,
Right.
right? The belief that the boldest engineering minds can solve the world's toughest problems for the benefit of people everywhere. I think that's your call to action, if you will.
Yeah, I think that phrase really resonates with me.
Yeah.
Where you need to have audacity, but you also need to have practicality of an engineer to solve those problems. It's not good enough to just have one of them. If you just engineering curiosity, then you go work on problems that are interesting, fun, but not really big. But if you only go after like big bold problems, then you're just going after big bold problem, but you're not necessarily making an impact. At Fourier, we are all about that fundamental friction or balance between boldness and practicality. And again, that's the kind of team, that's the kind of culture we want to build.
Yeah.
I think we've been largely successful until now.
Yeah.
It's actually a very interesting phase we are in, where we're about 14 people right now. We're gonna grow now that with this capital that we just raised, to keep that culture intact while scaling up is an interesting problem. At least personally, that's what makes me excited every day, because you kind of almost, it's a new problem, new hire you make every day.
So for someone who might be coming from a similar background as yours, say coming from like software tech or AI background and wants to take the leap of faith and go build a climate tech startup, what is like the first reality check you'll advise them on?
You focus on the economics. I think that's the main. It's great that you want to build bring together a societal impact, you can only bring it if you actually put together a business impact tightly aligned with it. The reality is many of these problems can be solved if you apply traditional regular business approaches to it. Oftentimes, again, we miss the point where you want to work on a climate problem, or you want to work on energy. You just look at the problem itself, and you shouldn't forget the main thing that you're supposed to do when you're starting a company is to talk to customers, to understand the market, to understand the problem, and then you go after it, which is what would be my advice for any company, any entrepreneur who's working on any problem, is to start with customers. And I mean, obviously, you'll have a vision, you have a technology, you have engineering curiosity, you want to work on a cool problem, but you have to start with an end value, a minimum product that can solve a specific customer. And I think that is true for this space too. You cannot just assume that okay, let's just build this problem, and then people will come. I think that's what people should be doing.
Well, Siva, this has been a fascinating conversation. Thank you for spending the time. This is truly an inspiring story of ambition meets pragmatism, and I can't wait to see what Fourier does over the next several years and hopefully decades.
Thank you, Kathy. I really enjoyed it. Thanks for putting this together.
Thank you.
Thank you.